Let us begin with the module on fiber optic link design. Previously, optical fibers are not used for communication. Telephone lines and coaxial cable are popular. But optical fibers are finding place in the communication industry. Basically, optical fibers are designed for the communication purpose only. The signal that is transmitted through the optical fiber is in the form of light, and therefore there is no effect of EMI or RFI. In telephone line or in coaxial cable, the signal is transmitted in the form of electrical, and therefore there is a possibility of disturbance due to EMI and RFI. In this module, we are not considering only these things, but how to design the fiber optic link by considering different aspects like optical power budget or the rise time budget, or called as the bandwidth budget. So let us see the things one by one. In this, we are also going to see how to choose, how to select the different components which are there in the link. Learning objectives. In this module, we are going to learn about the different transmission types, identify the elements in the network, identify the factors which affect the fiber optic link design, and also get familiar with the link budget considerations. Transmission types. There are two types of transmission. The first one is link, that is point to point transmission. And when we consider number of points to be interconnected, then it forms network. So in the network, they are again subdivided into point to multi points, means from a single point we are having multiple point connections. Mesh, that is a type of topology, and a ring, that is a type of another topology. Now elements of fiber optic link. When we consider the fiber optic link, that is from one point to another point or point to multi-point, the essential elements are, first is transmitter. That is, of course, we always require transmitter for that. And in case of fiber optic link, transmitter is nothing but some light source. So this can be a LED or it can be a laser. So for this we require what is the parameters that are associated with transmitter, and they are operating wavelength, that is lambda, line width, that is delta lambda, rise time, that is the time that is required to go up to a certain level, that is rise time, then bit rate, line format, and power level. Next essential component is fiber, of course. As we have seen in the previous modules, there are two types of fibers, single mode fiber and multi-mode fiber. In case of single mode fiber, the core radii is very small, which is of the order of say micrometers, say less than 10 micrometers we can say, and in case of MMF, that is multi-mode fibers, they are greater than the 10 micrometers. Then the fiber type we should know, that is SMF28, DSF, etc. There are other types of fibers also which are available. Then when we consider a fiber, then a loss that is associated with the fiber, because when we have a link using a fiber, then there is a possibility that there are couplings, coupling between the two fibers, coupling between the source, that is the transmitter, coupling with the receiver, etc. Spool length, that is, it is the length of the fiber which is continuous one. So that is the spool length that is associated with fiber. If we want to extend the fiber length further, the splicing is the technique that is generally used. Then receiver. Now when we say receiver, the two important factors associated with them is the sensitivity of the receiver and the rise time that is associated with it. That is P sense and rise time. These are the important parameters which are associated with the receiver. Receiver generally consists of some detector which converts the optical signal into electrical one. Then of course, as I have told you before, that when we have a continuous fiber, then no splices, no splicing loss also. But if we want to extend the fiber further for more than the spool length that is available, then splicing is required. So what is splicing is basically connecting the two fibers properly by matching their refractive indices, by having some proper alignment, etc. So if we have all these things properly, then the splice loss associated with it will be minimized. So what is the splice loss associated with it is also important when we have a connection. How many connectors are there? So connectors means coupling the source with the optical fiber. There we require some connectors. So what is the connector loss that is associated with it? That is also important when we consider the connection. Inline devices, they are splitters, filters, attenuators, amplifier, insertion loss should be considered here, and what is the gain of that amplifier has to be considered. So inline devices, they are important. So as we have seen that there are some elements which are associated with the fiber optic link. These are all essential elements, and we have to consider all the factors associated with these elements properly because we need to design it. Now when we consider such system, say for example, if you want to transmit the digital signal, then that is in the digital system, the important things are the data rate and bit error rate. And if you consider the analog system, then what is the bandwidth and signal to noise ratios. These are the important factors which we need to consider for digital systems, that is transmission of digital data as well as for the transmission of the analog signal. The main problems that are associated with them is the attenuation and some loss. So attenuation, that is reduction in the amplitude, and the losses which are associated with the attenuation has to be considered in both the type of systems. And of course predominantly dispersion is there for the digital systems. So what is dispersion? All of you are familiar, and that is called as the broadening of the pulse. So when we try to design the fiber optic link, then the factors for the evaluation of fiber optic link design has to be considered. So let us take one factor at a time and discuss it in detail. So let us start with the type of the fiber. So when we want to establish the fiber optic link, which type of fiber you want to use. So whether you want to use the single mode fiber or a multi-mode fiber. So depending upon the application, you have to choose it. Then another thing is operating wavelength. So the wavelength at which the data is being transmitted, or the wavelength of the light that is used. And for the optical fibers, the typical wavelengths are 780 nanometers, 850 nanometers, 1310 nanometers and 1550 nanometers. These are the typical wavelengths which are used, and these wavelengths are specified here because for these wavelengths there will be a minimum loss which we call as the attenuation loss or the dispersion loss that is associated. So that is why these wavelengths are important. Then the power of the transmitter, and this power is generally expressed in dBm and source type. So whether we are using the light emitting diode, what is its wavelength, then laser diode, etc. What is the sensitivity of the receiver and overload characteristics which are associated with them, and they are generally expressed in dBm. Type of the detector, like similar to we have a source type, that is LED or laser. Accordingly we have to choose whether it is PIN diode or avalanche photodiode or IDP. Modulation type, that is whether the modulation to be used is amplitude modulation, frequency modulation, pulse code modulation or digital modulation. Bit error rate, that is BER, it is generally applicable for digital systems only. Typically their values are 10 raised to minus 9 or 10 raised to minus 12. Signal to noise ratio, it is generally specified in dBm. Number of connectors, as the number of connectors increase, loss also increases. Number of splices, as the number of splices increase, loss also increases. Environmental requirements, like what is the humidity, temperature, exposure to sunlight, these are the considerations for the environmental requirements. Mechanical requirements, flammability, indoor and outdoor applications, these are the considerations for mechanical requirements. Now let us begin with the actual elements in the design of fiber optic link. So optical transmitter, or another name for them, are the sources. We know that there are two basic sources which are optical sources. They are LEDs and lasers. Now what are the characteristics of these LEDs, that is light emitting diodes? First of all, we have to see what is the output power, what is the modulation bandwidth, center wavelength, spectral width, source size and far field pattern. These are the important characteristics of LED. Next optical source that we can use is laser. That is, we know that laser should have the following characteristics, like what is the output power, modulation bandwidth, center wavelength, number of modes, chirp, line width, mode field of the Gaussian beam. So these are the characteristics of laser, that is light activated stimulated emission of radiation. Next element that we have to consider is optical fiber. If we are using multimode fiber, then following characteristics are important. Attenuation, that is reduction of amplitude when the signal is passed through the fiber. Multimode dispersion, that is the broadening of the pulse when a pulse is transmitted through the multimode optical fiber. Chromatic dispersion, this dispersion is generally wavelength dependent. Numerical aperture, that is the light capturing ability of that particular fiber, and of course the last one, that is the core diameter. So what is the diameter of the core that decides whether it is a multimode fiber? So multimode means more rays can enter into the optical fibers. On the other hand, if we consider a single mode fiber, the factors associated with them are similar to that of the multimode fiber with a slight difference. We should know the attenuation, of course. Here there is no dispersion as such due to the number of modes, because it is a single mode fiber, but chromatic dispersion may occur. We should know the cutoff wavelength and what is the spot size. Next element is optical receiver or detector. The job of optical detector or receiver is to convert the light signal into the electrical signal. So the response of the optical detector is important depending upon what is the wavelength range, then the rise time associated with it, the bandwidth that is associated with it, the saturation level and the minimum detection level. So, all these factors are very much important when you select the optical receiver or detector for fiber optic link. Simple fiber optic link. Look at the diagram. In the diagram, the first block is TX, that is transmitter. Fiber optic link is coupled to the transmitter and then it is given to the input of optical amplifier. This optical amplifier amplifies the optical signal which is coming from the transmitter. This amplification is required because there is a possibility of attenuation when the signal is transmitted through the fiber optic link. This optical link is then completed when it is received at the receiver section. When the data is transmitted through this link, again there is a possibility of attenuation and hence again optical amplifier is required at the other end. Now the amplified signal is transmitted through the fiber optic link to the receiver part. So in the receiver we have photodetector which converts this light signal into electrical form. In the transmitter side we have LED or laser which converts the electrical signal into optical form. So these are the different devices which are used in simple fiber optic link. The medium of communication is optical fiber. Link budget considerations. Link budget is necessary in order to manage the input power and the output power, as well as there is a rise time or bandwidth budget. So there are two types of budget. The first is the power budget and the second is the rise time or bandwidth budget. Let us first see what is power budget. What are the requirements of the power budget? The received power should always be greater than or equal to the minimum power at certain bit error rate. Then and then only it will be properly detected, or we can say that the information is properly conveyed. The formula for PRX is PTX minus total losses plus total gain minus P margin. Here PTX is the transmitted power. The total losses include the coupling losses, attenuation, bending losses, dispersion losses. All these losses are included in this total losses. Total gain, which is achieved due to the optical amplifiers or electronic amplifiers which are there in the system. And P margin is some offset that is kept, and generally it is 6 dB. These losses which we have considered earlier, they are L is equal to LIL plus L fiber plus L connectors plus L nonlinear. So what is LIL is the insertion loss, fiber loss, then connector loss is there, and L nonlinear is nonlinear loss. Similar to that, when we have a gain, the gain is due to amplifier as well as there is a nonlinear gain. So gain amplifier is amplifier gain and G nonlinear is nonlinear gain. Generally, this power is expressed in dB or dBm or microwatt. This dB is equal to 10 log to the base E of P1 upon P2. So if the dBm value is 0.0, percentage of 1 milliwatt is 100. Power 1 milliwatt, and it is generally used in laser peak output. It is a typical laser peak output. If dBm value is minus 13, it is 5% of 1 milliwatt, power is 50 microwatt, it is typical pin receiver sensitivity. If dBm value is minus 30, then it is 0.1%, that is 1 microwatt, typical APD receiver sensitivity. If it is minus 40, 0.01%, 100 nanowatt and typical LED peak output. Now, how to convert this decibel to power? If we have 1 dB, then power output as the percentage of power input is 79% and therefore the percentage power lost is 21%. If it is 2 dB, then 63% power output with 37% power lost. If it is dB3, then 50% power output with 50% power loss, that is called as the half power. If dB4, then 40% of power output and 60% power lost. If dB5, then 32% power out, 68% power lost. If dB6, 25% power out and 75% power lost, that is 1/4 the power. dB7, 20% power out, 80% power lost, 1/5 the power. dB8, 16% power out, 84% power lost, 1/6 the power. dB9, 12% power out, 88% power lost, 1/8 the power. And dB10 means 10% power out and 90% power loss, so 1/10 the power. If dB is 25, then the power out is 0.3%, so the power lost is 99.7, that is 1/300th of the power. If it is 30 dB, 0.1 power output, 99.9 power lost, 1/1000. 40 dB, 0.01% power output of the power in and 99.99 power lost, that is 1/10,000 of the power. And 50 dB means 0.001 power out as percentage of power in and percentage power lost is 99.999, that is 1/1 lakh. Now, let us take one example, that is how to have the power budget calculations for long haul transmission. Long haul means long distance communication system. Let us consider two buildings, building 1 and building 2, which are at much far distance from each other. Now, let us calculate the power budget for this system. Consider Ptx as 0 dBm, so there is no loss, and at the receiver side the sensitivity, that is P sense, is minus 28 dBm. We want to establish a fiber optic link between them. There is a connector required at the receiver side as well as at the transmitter side. There are 4 splices as you see in the diagram. The distance between them is say 185 kilometers. The dispersion coefficient D is equal to 18 ps per nanometer kilometer. Number of splices are 46. Splice loss is 0.1 dB. Connector loss 0.2 dB. Margin 6 dB. Attenuation coefficient alpha 0.25 dB per kilometer. So, is this a good system? Ptx 0 dBm, P sense minus 28 dBm. With all these considerations, what we have to see that how to design this as a good system. Now, let us analyze the different parameters. The first and the important parameter is the fiber loss. The fiber loss is 0.25 dB per kilometer into 185 kilometer, where 0.25 dB is the attenuation loss and 185 is the total length of the fiber. So, the fiber loss is 46.3 dB. Splice loss 0.1 dB into 46 because there are 46 splices. So, 4.6 dB. Connector loss 0.2 dB into 2. There are two connectors, one at the transmitter and another at the receiver. So, 0.4 dB. So, what are the total losses? They are the addition of 46.3 plus 4.6 plus 0.4, that is 51.3 dB. P margin is 6 dB. PRX is equal to minus 57.3 dB. Here you can see that the PRX, that is the receiver side power, is less than the P sense, because what is the P sense value is minus 28 dB. So, here you can say that this system is not much good system. So, it is a bad system. Now, what is the solution for this? The solution is one has to place an amplifier, but if we want to place an amplifier, what will be its gain value and where is the location of that particular amplifier? So, let us first calculate the gain. This gain should be greater than or equal to P sense minus PRX, that is minus 28 minus minus 57.3. So, it should be greater than or equal to 29.3 dB. To make it easy, let us consider the gain should be greater than 30 dB. Now, where to put the amplifier? So, we get the value of the gain now, but where to put the amplifier? Amplifier location. Power amplifier at the transmitter, pre-amplifier at the receiver, in line, that is at any point along the fiber. Now, one has to analyze the system for fixing the location of this amplifier. If we consider the power amplifier, then PTX plus gain is equal to P out. PTX is 0, gain we have considered it as 30. So, the output power P out is 30 dBm. But is there any power amplifier with 30 dBm P out? No, there isn't. Hence, the use of power amplifier is not there. Now, whether we can use pre-amplifier? Now, let us see where the pre-amplifier location is. Remember, P out received is equal to minus 57 dBm. Pre-amplifier with 30 dB available? Yes, it is available. But can it take minus 57 dBm? No, it cannot take. Hence, we cannot use pre-amplifier. 30 dB gain amplifier available here. But what value can it take? Typically minus 30 dBm. So, in-line amplifier is the most useful amplifier which can be placed along the length of the fiber at any point. Now, we can find the location. Now, where is the minus 30 dBm point? PTX minus loss at that point is equal to 0 dBm minus 30 dB. So, loss at that point is equal to minus 30 dBm. Assume other losses as 0. Loss at that point is equal to fiber loss. So 30 is equal to alpha into the length of that point. Remember, alpha is 0.25 and the point length is 30 upon 0.25, that is 120 kilometer. But 120 kilometer from transmitter, number of splice is equal to 120 upon 4, that is equal to 30. Splice loss is 0.1 dB into 30, that is 3 dB. Fiber optic link design procedure. Also remember connector loss at the amplifier and transmitter. Two connectors, one at transmitter. The connector loss is 0.2 dB into 3, that is 0.6 dB. Actually, at 120 kilometer, total losses is equal to fiber loss plus splice loss plus connector loss. So 30 plus 3 plus 0.6, that is 33.6 dB. 33.6 dB is greater than 30 dB. So it is not good. Now we have excess of 3.6 dB. So find the distance. Fiber loss length is equal to 3.6 upon 0.25, that is 14.4 kilometer. Good location is equal to 120 kilometer minus 14.4 kilometer, that is 105.6 kilometer. At 105.6 kilometer from TX, that is transmitter, fiber loss is equal to 0.25 into 105.6, that is 26.4 dB. Number of splice at 105.6 kilometer is equal to 27. Splice loss is equal to 0.1 into 27, that is 2.7 dB. So total losses will be 26.4 plus 2.7, that is 29.1 dB. 29.1 dB is less than 30 dB. So now we can confirm that 105.6 kilometer is the good location. So this is all about the power budget. Now let us go to the bandwidth budget. System rise time. First, calculate total rise time considering the transmitter, fiber and receiver. Calculate the fiber rise time as T fiber equal to D into delta lambda into capital L, where D is the dispersion coefficient, delta lambda is line width and capital L is the fiber length. Tx rise time, that is Ttx, is equal to given by generally the manufacturer, and the receiver rise time is also normally given by the manufacturer. Total rise time T system is equal to 1.1 into bracket Ttx square plus Trx square plus T fiber square raised to half. So if we consider the system as such, then if the transmitter is sending the digital data, that is the pulses, then they are properly amplified using optical amplifier, transmitted through the fiber, and at the receiver end we can see some dispersion effects as shown in the figure. For good reception of signal, T system should be less than or equal to 0.7 into pulse width, that is PW. PW is equal to 1 upon bit rate for NR0, that is not return to 0, which is equal to half bit rate for return to 0. Rise time budget measurement for long haul system. Let Tx rise time be 0.1 nanosecond, Rx rise time 0.5 nanosecond and the line width delta lambda 0.15 nanometer. Dispersion coefficient D is equal to 18 ps plus nanometer kilometer. Fiber length 150 kilometer. Bit rate 622 Mbps and format Rz, that is returned to 0. Rise time calculation. Fiber rise time Tf equal to length into d, that is dispersion coefficient, into line width delta lambda, that is equal to 150 kilometer into 18 into 0.15 nanometer, that is 0.4 nanoseconds. Therefore, total rise time, that is T system, is equal to 1.1 into square root of TLS square plus TPD square plus TF square, that is equal to 1.1 into square root of 0.01 plus 0.25 plus 0.16, that is equal to 0.77 nanosecond. Let us say bit rate is equal to STM4, that is equal to 622 Mbps, and format RZ. T system less than 0.7 into pulse width. Pulse width is equal to 1 upon 622, that is equal to 1.6 nanosecond. So 0.77 nanosecond less than or equal to 0.7 into 1.6 nanosecond. 0.727 nanosecond is less than 1.1 nanosecond. So it is a good rise time budget. But if we consider bit rate as STM16, that is 2.5 Gbps, then the T systematic less than or equal to 0.7 into pulse width. Pulse width is 1 upon 2.5 into 10 raised to 9, that is 0.4 nanosecond, and 0.77 nanosecond is greater than 0.28 nanosecond. So it is a bad rise time budget. So budget summary: source LED versus laser diode. Options for the delta lambda are 850 nanometer, 1310 nanometer and 1550 nanometer. For 850 nanometer, power budget is mediocre, bandwidth budget bad, financially it is cheap. For 1310 nanometer, power budget good, bandwidth budget good, financially less expensive. 1550 nanometer, power budget very good, bandwidth budget also very good, but it is expensive. Modulation bandwidth: LED, power budget not applicable, bandwidth budget bad, financial cheap. LD, NA, that is not applicable, good and expensive. Output power LED, power budget mediocre, not applicable, cheap. Laser diode, good, not applicable, expensive. Radiation pattern LED, far field pattern, not applicable, bandwidth budget bad, financially cheap. And Gaussian beam for laser diode, not applicable, good and expensive. Fiber attenuation, multimode, power budget mediocre, bandwidth budget mediocre, financial cheap. Single mode, power budget good, bandwidth budget good, financially expensive. Dispersion, multimode fiber, power budget mediocre, bandwidth budget mediocre, financially cheap. Single mode fiber, power budget good, bandwidth budget good, but financially expensive. Numerical aperture, multimode fiber, mediocre, bandwidth budget mediocre, cheap. Single mode fiber, good, good and expensive. Core diameter, multimode fiber, mediocre, mediocre, cheap. Single mode fiber, good, good and expensive. Receiver pin versus APD. Rise time or bandwidth for pin, mediocre, mediocre, cheap. APD, good, good, expensive. Response wavelength range, pin photodiode, mediocre, mediocre, cheap. APD, that is avalanche photodiode, good, good and expensive. Saturation level, pin, mediocre, mediocre, cheap. APD, good, good, expensive. Minimum detection level for pin photodiode is mediocre, mediocre, cheap. APD, good, good and expensive. Now let us go to the sensitivity analysis. Minimum optical power that must be present at the receiver in order to achieve the performance level required for a given system is the sensitivity. Factors affecting the analysis. Source intensity noise. It refers to the noise generated by the sources, that is LED or laser. Phase noise, the difference in the phases of two optical wave trains separated by time, cut out of the optical wave. Amplitude noise caused by the laser emission process. Next is the fiber noise, relates to the modal partition noise, and the receiver noise, it is the noise which is generated in the photodiode or conversion resistor. Fourth one is time jitter and intersymbol interference. Time jitter is a short-term variation or instability in the duration of specified interval. Intersymbol interference result of other bits interfering with the bit of interest. It is inversely proportional to the bandwidth. Are diagrams to see the effects of time jitter and intersymbol interference. These diagrams are used to see what are the effects of these two factors. Bit error rate. It is the main quality criteria for digital transmission system, and it is given by BER is equal to Q into bracket I mean square upon 4 into N0B, where N0 is the noise power spectral density, I mean is the minimum effective signal amplitude, B is the bandwidth, and Qx is the cumulative distribution function, that is the Gaussian function. So if you look at the diagrams, these are the eye diagrams. Ideal eye diagram is shown in the figure A. If there is a time jitter, then it is as shown in the B. You can see the whatever are the lines, they are thick. Intersymbol interference, then these lines get doubled, and if both they are present, then the lines are doubled as well as they become thick. Next is signal to noise ratio, which is called as SNR. S represents the information to be transmitted, that is signal, and N integration of all noise factors over the full system bandwidth. And SNR in dB, it is expressed in dB and is given by 10 log to the base 10 of S upon N. Cost or performance considerations. Component considerations such as light emitter type, emitter wavelength, connector type, fiber type, detector type, etc. has to be considered when we see the performance of the system. Let us summarize the module on fiber optic link design. Initially, we have started with the types of transmission. They are link or network. Link means point to point and network means number of points to be interconnected. In fiber optic link design system, there are number of elements like transmitter, optical fiber, optical amplifiers and receiver. Optical amplifier may be required at transmitter side as well as at the receiver side. The power budget and bandwidth budget are the two important budgets that are required to be considered while designing the system. The examples are considered here for long haul communication system design. And here we have not only calculated the power budget but also identified the location of the different components which are there in the system. In the rise time also, we have analyzed the system accordingly so that the number of losses should be considered for measurement of these budgets. Finally, in this case, we have calculated what is the performance associated with this fiber optic link. The elements which are responsible for the performance analysis are listed.